Hello everyone and welcome to this next lecture on Python Power Electronics, and this is a continuation of the series on control functions, and in this lecture I'm going to talk about time event variables. So as usual, I'll start off with my website pythonpowerelectronics.com. In this we go down to the section downloads. In downloads I go to papers, and in papers I open up two files. The first is control structure.pdf, which I've been using in the previous lectures, and the new one is timing scheduler, because this is about timing. So control structure is basically something which I've used before, and in this I'll be talking about this last variable. I mean, it's not the last, I still have one more, but I'll be talking about this one, time event. So time events can be described in much more detail in this lecture, in this paper. In this paper I talk about how the simulator schedules every control function. Now when I say schedule control function, what it means is, in any circuit there are usually two different types of controls that you can use, two broad categories. The first is analog control, which you can use using analog circuits. You usually use them using operational amplifiers, oscillators and all those things. The second R is digital control. When I mean digital control, I mean microcontrollers, digital signal processors, FPGAs, Arduinos, Raspberry Pis, all those. Now the difference mainly is in the fact that with an analog control you have continuous control, which means the control is almost always present. You have always measurement, you have always processing, you have always feedback. There is always a control action. In digital signal processing, that's not the case. The reason is because your processing happens digitally, and when the processing happens digitally, the minimum requirement is you need to convert your analog measurements to digital form. This analog to digital conversion takes some amount of time, right? Which means your sampling period, the discrete time, the time period of sampling has to be greater than this analog to digital conversion period, or else you have inaccurate data. So for that reason, almost every one of these type of controllers, like DSPs, FPGAs, microcontrollers, will always have discrete control, and that discrete control is usually adjustable. Sometimes it's fixed, sometimes it's always changing. There are different ways, but what's important for us is, in this circuit simulator I mainly consider discrete control. I do not talk about analog control. So there is no operational amplifier, there is nothing. There are some passive circuits like the resistors, capacitors, so you could build, technically you could build something out of it, but I would strongly discourage you from doing so. I would suggest, when you want to use this circuit simulator, try to build all your controls using discrete time. So in this I'm going to talk about that. And for when you talk about discrete timing, what is important is time scheduling. So for example, in the previous ones, I'll jump over to my this is the control file which I had, and let me go over here. This is the control function. So basically this control code is inserted into the function. Now if you notice here, this entire thing, it has nothing special on timing. So this control code we've written executes at every time instant of the simulation. So the time instant of my simulation is 1 microsecond, which means that this control code runs at a frequency of, is a time period of 1 microsecond. Now that's usually not desirable. You do not want to run control functions at very high speed like 1 microsecond. 2, you want this to be realistic. In real life, your control functions are going to be much slower, or sometimes can be faster, but you want these to reflect. You don't want just to have no control over the time event at all. And for that reason, I have what this is called time event. So let me jump over and let me start my circuit simulator. So as usual, I go into my virtual environment. Now I activate my virtual environment. So and this is it. Let me just verify. Yes, it is. And now that I'm in this, I will go into my web application, and I will run my server. For details on this, please visit any of the previous lectures. I won't talk about it here. So this shows the server is running, and all I have to do now is go over to my web browser and open this server. So I shall do exactly that. It has been saved. So I go to simulation library. So far there is only one simulation because that's what I started off with. I load the simulation. I don't have to change any of these things. I just keep going. Add circuit file, nothing to do. So just process. Important thing, you must process it because I'm launching it for the first time after launching the simulator. Back to main page, edit circuit parameters. Again, nothing to change here. Go back to main page. Now finally, edit control. This is where I come. So let me come down here. I'm not going to change control outputs. We have one particular static variable. That's okay. Now what I am going to do is I'm going to now add a time event. A time event, when I click on this button, it's going to come back to this time event. As usual, what is the name of the time event variable? Now this can be anything. You can call it T event, T1, T2, T control, anything. Do not name it T clock. Whatever you do not name it T clock, because T clock is a reserved word, and I'll come down to this later. So I will come to, let's call this T control 1. Let's be a little more specific. The initial time event, let's say 0.0. What this means is once the circuit simulator launches, this will be the first time event at which this control function will execute. So whenever you specify a certain time control value, when this variable takes on a certain value, what this means is the simulator guarantees that when the time instant of the simulation is greater than or equal to this value, it will execute the control function. Alright, so let me just save this for now. So now that we have this, I don't think we need anything else for now. Let me now go back and go to the main page. So let me come down here. Actually, let me run the simulation and let me show you what happens. I haven't done anything, so I don't expect an error or expect anything. Now simulation is running. There is no error, so everything is okay. Let me, as usual, go to this control function. So you see here, there is now this function called T control 1. This is what we've defined. And you see here, it is taking in a value from the interface time, pause, whatever. This doesn't matter. This is an internal variable in the circuit simulator. So every time you define a time event variable, the simulator creates an internal variable, and at initial time it takes the initial value that we've defined. In this case is 0.0. You can always change it. So when the function starts, it assigns the existing value to our variable that we've defined. So our variable now has the previous value, has the updated value of time event. And eventually, when we do continue with this, that is when we are about to exit the function, it does the reverse. That is, it stores the value of T control 1, whatever is the time control variable that we've defined, back into the internal variable that circuit simulator uses. But something else happens. You see here, it says system T events append T control 1. What this means is it is now updating, it is adding this latest value of T control 1 to a system events variable. So this way, the circuit simulator collects all these events which are created, and one of the events, of course, is the simulation integration time instant. And in this manner, the circuit simulator guarantees that whichever is the first event generated, it could be the integration time event, or it could be something generated by a control function, the simulator will guarantee that then every control function is executed at that time instant. Alright, so anyway, for more details on this, read the paper. That is, read this paper, Timing Scheduler. I won't go into too much details in this lecture. So now let's stop the simulation because nothing much is happening. And now let's try using this variable that I've defined. So it is tcontrol1. Now the way it is this, like I said before, actually I will add this here. tcontrol1 is our variable, and this starts at an initial value of 0.0. Now how do we update it? We update it, we have another variable called tclock. Okay, this is a reserved variable that I am providing you through the circuit simulator. So the circuit simulator will give you the current time instant of simulation. So whatever is the time instant of simulation when this file is being executed, that is available through tclock. So now that we have this, we can run a conditional statement. What I can say is this: if tclock is greater than equal to tcontrol1, execute a certain block of statement. So I can say here, this is my control block which should be executed in discrete time. Okay, so here I put in all what I need to be executed as a discrete controller, and eventually everything will come in here, but I'm going to take it step by step. So what does it mean? When the time is, so let's say for example at initial time value, alright, when time is 0, if tclock, simulation starts at 0, so tclock is also 0. If tclock is greater than or equal to tcontrol1, execute this block. So initially it will execute. After executing, what happens? I execute my control block. Then what do? I must update the value of tcontrol1. Alright, so let's say I call this tcontrol1 plus equal to, and I give it a value. I can give this any value. You know what I'll give this? I'll give this a value of 1 millisecond. Alright, so I am saying that I am going to have a control block which runs every millisecond. My simulation runs at 1 microsecond. I am running this at every millisecond. I can change it. I can change this. I can do whatever I want. So this is up to you. So when you are doing your simulations, you can match whatever is happening in your digital signal processor or your FPGA by changing these values. So you can have every control function execute when you want it to execute. Now let's continue. What does this actually mean? Let me now take one of these values and show you how it makes a difference. Let me do this, or let's say we have the iSource one. I am now going to take, let's add another variable. So let's go back to the main page. Let's go back to edit control, go back to configure control, and let me add another variable storage element. So I'm going to add another variable storage element, and I'm going to call this store var 4, and let's again give this a value of 0.0. Let's say yes. The only reason I'm now trying to plot this latest variable, I'm going to plot something which is specific to time domain, that is my discrete time. Let's go back to main page, view output. Let's wait for this. So what am I going to do here? What I am going to say is, here typically there would be a lot of control code. I'm not going into the control right now. I'm just telling you about the variable. So what I'm going to say is, I'm going to say store var 4 is equal to iSource 1. Alright, what am I doing here? I am running this block at 1 millisecond. This outer block this entire function runs every microsecond. So I am doing a sampling of this ammeter source current. That's what I'm going to do. And let me see now with this sampling how this variable looks with respect to, let me now remove this iSource1. So let me now show you how store var1 compares with store var4. Store var1 measures the exactly measured output current, or rather the source current. It measures the instantaneous value of the source current. This one measures the sampled value of the source current. So let's see how these two differ. So let me run the simulation. Simulation is running. As always, go here, check if there's an error. There is no error, so now we know it's running actually. And we come down and I shall add another plot. And this plot, I shall call it var store 4. Let's start this plot. So we should call this add waveform. Click on the add waveform. I need to add two variables. I need to add store var1. Let's go back and check if that is indeed the case. Yeah, I'm adding store var1 because that stores the value of the source current. So let's call this inst val save waveform, and let's add another waveform, and this value will be store var4. Let's call this sample. Just this legend doesn't mean anything, it's just what appears on the plot. So let's save this plot and let me plot this. So it has plotted. Let me go over to my file browser and let me go to virtual environment, diode rectifier. So there is now a store var4. So you see what has happened. Alright. Now you might think there's a mistake. Actually, it's not a mistake. Let me zoom in on one distance. So let me zoom in between 0.25 and 0.4 because I need to know exactly what's happening. So I'm going to zoom in between 0.25 and 0.4 and let me plot this again. Okay, it has plotted, so let me come back. No, that wasn't the value. Oh, I think I made a mistake in the range. It's 0.025 to 0.04. Yeah, we are not there yet, so it's 0.025. That's wrong. If you put in a wrong range, it will just plot everything. Remember that. So it will not give you an error, it will just plot the entire range. So it should be 0.025 and 0.04. Okay, let's hope I got the range right this time. And yes, I did. So you see what's happening here. It is the sampling happens at discrete events. You see here, it's happening at 0.36. It's happening at 0.37. This is 0.37. So it's happening every millisecond. Happens at somewhere at 0.038, again 1 millisecond. So it is picking up these values, and between that it remains constant. Why? Because once I sample, I don't touch this code. Remember, come back here and look at this code. Once I enter this code, I am sampling this value of source current. I am updating T control, which means this block will not execute for another 1 millisecond. Alright, it will execute only when T clock exits T control. So let's suppose in the beginning T clock is 0. I execute this code. T control becomes 1 millisecond. T clock will not, this block will not execute until T clock is equal to 1 millisecond. And when this block executes, T control becomes 2 milliseconds. So this block again will not execute until T clock is 2 milliseconds. So this way I have scheduled this block to be executed only when every 1 millisecond. It will not execute between that. So that's what happens. Between these samples, it remains constant. So we can actually play around with this. Let me show you what happens. So let me now reduce this to 100 microseconds. Let me see how it works. You will see a slightly different waveform. Let me stop the simulation. Let me run it again. Simulation is running as usual. Go to the command line, check if there's an error. There is no error. So now we can go to the file browser. Okay, actually we don't go to the file browser because I haven't done it. So let me go back and run this. As usual, I want a range and I shall plot the latest plot. So let me go back here and now I can click this fig file. So here you see a very different plot appears. Now you see what happens. Oh, okay, because again actually it was too soon. So this is still pretty clear because the simulation didn't run for so long, so the range was invalid, so it just plotted everything. That's what happened again. You see, it is a stepped waveform. The orange waveform is sample. The blue waveform is instantaneous. The orange waveform is a sample of the blue waveform because I am sampling every 100 microseconds. And between two samples, the value remains constant. Why? Because I'm not touching the sample again. This is what discrete sampling does, and this is what time event variable does. Now, just to notice, you can have multiple time events in a single variable, in a single file. So you can actually add T control 2, T control 3, several others, do all kinds of complex control. It's totally up to you. Only one thing to remember. When you define a time event variable, okay, T control 1, whatever you define, you can define 10 of them, 100 of them, no problem. If you define a time event variable, do not forget to update it. Do not forget to do this. If you do not update a time control variable, it will default. Supposing I don't do this, alright, let's see what happens. What will happen is this block will never execute, so you will never get ST4. So you might actually think your control is broken. Your control is not really broken, but it's just that this block won't execute. In general, I would say it is bad practice to have a time event variable and not update it. The reason is not just because there's a reason. Like I said, for details, go over and read this paper. I think it's a pretty interesting paper. It tells you how this circuit simulator schedules time events. So I would suggest have a look at this paper at one point of time. But in brief, if you do not update a control event variable, if you do not event a time event variable after defining it, it will default to the integration time step. And when it defaults to the integration time step, what happens is it could mess up other control functions that you have. Alright? And that's a problem. So that's the only thing you need to look out for. Otherwise, everything else is pretty much straightforward. Remember, do not define any control variable as T clock. This is a reserved keyword. If you define it, you may lose this value and it will completely screw up your control. So don't do that also. Other than that, I think that's more or less it for this lecture. As before, I will stop this lecture here. Otherwise, I don't want a very long lecture. So I will stop this lecture. The next lecture will be not on a time event, but I'm going to describe another concept, that is how we can have multiple control functions in a single simulation and how we can actually connect these control functions together. So that will be the topic of my next lecture. For now, I'm going to end this lecture. Thank you so much for watching, and I hope to see you soon. I don't know when the next lecture will be, but stay tuned and thank you again. Goodbye for now.